Hey, JSOS, Jahanzib here. So, today I want to talk about black holes and a journey through one. In order to understand what transpires when you go through one, I first need to tell you what a black hole is. So, what is a black hole? A black hole is an object that has an absurd amount of mass crammed into a relatively tiny space. Once something gets sucked into a black hole, it is unlikely that it will escape, since even light is unable to escape a black hole once it is trapped in it. There are five main parts that make up a black hole. These are the event horizon, singularity, photon sphere, ergosphere, and innermost stable circular orbit, also known as ISCO. The event horizon is the theoretical boundary around the black hole where matter and electromagnetic radiation and light can pass into the black hole but cannot escape it. The singularity refers to the center or the eye of the black hole, and the curvature of the black hole becomes infinite at the singularity. The photon sphere is a spherical boundary that does not have a definite or classified thickness. Photons move perpendicularly to the sphere, and it is trapped in an elliptical orbit with respect to the black hole. The ergosphere is the area where things are always moving due to the phenomenon of frame dragging. Frame dragging is an effect on space-time predicted by Einstein's general relativity equation. This is due to the non-static stationary distributions of mass and energy. The final part is the ISCO, and this is where objects orbit the black hole at certain distances from the singularity. Black holes fundamentally have three properties: mass, electrical charge, and spin due to angular momentum. Due to the way that black holes are formed, the electrical charge will be close to zero. Angular momentum is the quantity of rotation of a body, which is the product of its moment of inertia and its angular velocity. There is quite a bit of history behind black holes. They were first explained by Einstein's theory of relativity. However, they were first theorized by 18th century scientists Jean Michel and Pierre-Simon Laplace. Although this idea was ignored by most 19th century scientists, there were some whose curiosity or even belief urged them to discover more. The first modern solution of general relativity that would characterize a black hole was found by Karl Schwarzschild in 1916, although its interpretation as a region of space from which nothing can escape was first published by David Finkelstein in 1958. There are five types of black holes: primordial black holes, miniature black holes, stellar black holes, intermediate black holes, and supermassive black holes. Black holes can start small, and by sucking in things from the universe around them, such as dust and gas, they can grow to be larger and larger. Primordial black holes are thought to be formed shortly after the Big Bang, and are the seeds for supermassive black holes. Miniature black holes are also called quantum mechanical black holes and are thought to have a mass smaller than our Sun, and are also thought to be formed early in the history of the universe, just like primordial black holes. Stellar black holes are formed once the core of a high-mass star completely burns to iron. The energy production and reactions that have been taking place in the star come to a stop. Following that, the core of the star collapses in on itself rapidly and explodes in what is known as a supernova explosion. Intermediate black holes can also form by smaller black holes sucking in white dwarfs and other celestial objects. Scientists suspect that intermediate black holes are rare because most black holes have grown. That allows us to effectively transition into the most abundant type of black hole, which is the supermassive black hole. Over time, black holes trap more and more objects, or huge supernovas, or colliding with stars to become supermassive black holes. Since the universe is currently very old, many black holes have had enough time to grow to become larger and larger. They grow by accretion of matter and merging with other black holes. Accretion is when matter gets attracted to one center due to gravity, and the matter continues to accumulate at a greater rate as the force of gravity increases. Therefore, most black holes in the universe are under the classification of supermassive black holes. Another possibility that has been theorized is that large gas clouds could collapse into a quasi-star. The quasi-star collapses to form a black hole. It becomes unstable to radial perturbations because of electron-positron pair production in its core, and the collapse into a black hole can occur without the need for a supernova explosion. Supermassive black holes also exist at the center of every galaxy. The one at the core of the Milky Way is called the Sagittarius A. Some galaxies consist of two supermassive black holes called a binary system. That effectively allows us to transition into our next subject matter: the detection of black holes. The essence of black hole detection lies in the manner that black holes treat its surroundings. Supermassive black holes drive active galactic nuclei and galactic jets. Active galactic nuclei refer to the extremely luminous center of some galaxies. Instead of being thermal energy, the energy emitted is actually in the form of X-ray, radio, ultraviolet, and optical radiation. In the case of galactic jets, the magnetic field of the supermassive black hole and the accretion disk interact, and this interaction simultaneously releases energy from the black hole. This release is constrained to one direction and causes the energy to be funneled and released like a jet, hence the name galactic jets. Another method is made possible through our understanding of the electromagnetic spectrum. The electromagnetic radiation can have different wavelengths, and that, among other things, is what determines where a wave lies on the spectrum. These waves of light can be used to detect a black hole through the detection of the effects of the black hole. When anything enters a black hole, it accelerates rapidly and heats up. The matter funnels around the singularity due to gravity. The atoms that make up the matter ionize, and once the temperatures reach a few million kelvins, X-rays are released. By using special telescopes fitted with special lenses, scientists and observers can see the X-rays being emitted from the black hole. The emissions, however, are not constant, since what goes into a black hole and how often it does is not uniform. Another way to detect black holes is through the way it treats light. A black hole can bend light in certain circumstances. If light passes far enough from the black hole that it does not get sucked, but it's still close enough that the light wave experiences a great deal of pull from it, the light gets bent by the black hole. At that time, if an area in space is observed and there is a distorted appearance, we can tell that there is a black hole there. In addition to a distorted look, there will also be the sight of multiple images and duplicates. This phenomenon in scientific terms is known as gravitational lensing. That being said, an advanced way to detect black holes that is available right now is to use gravitational wave ripples. Whenever neutron stars or another black hole is consumed by a black hole, these ripples are sent out. The merging of black holes also causes these ripples. There are two ways to detect these ripples. Scientists set up two stationary probes in outer space apart from each other, and if a ripple passes by, the probes vibrate indicating the black hole's location. The second way is to shine a laser light at a detector, and when the ripple comes, the laser will move around. LIGO is an observatory that detects this. These indications of gravitational waves reveal the location and existence of a black hole. Okay, let's delve into the mathematics behind a black hole. We will mainly be discussing Albert Einstein and Karl Schwarzschild. In 1905, Albert Einstein determined that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum was independent of the motion of all observers. This was the theory of special relativity. It introduced a new framework for all of physics and proposed new concepts of space and time. Einstein then spent 10 years trying to incorporate acceleration in the theory and published his theory of general relativity in 1915. In the theory, Einstein stated that he determined that massive objects cause a distortion in space, which is felt as gravity. The famously known equation for energy by Einstein, E=mc², is part of the mathematical evidence. This equation proves the fact that nothing can escape a black hole. The equation shows how much energy would be in a specific amount of mass, and so as I was saying, the equation shows how much energy would be in a specific amount of mass, and that is essential to the mathematics behind a black hole. The equation dictates that with speed, mass also increases, and at maximum speed, which is the speed of light, the mass of the object would be infinite. If the mass of an object is infinite, then it would require an infinite amount of energy to move that object, consequently capping the maximum speed any amount of mass can achieve. The fastest moving things in the universe, photons, are light particles that move at the speed of light, and are only able to do so because they have a mass of 0. However, even photons cannot escape a black hole, and that effectively proves that nothing can. Okay, let's talk about Einstein's general theory of relativity. The equation essentially calculates the information regarding how a specific amount of mass and energy warps space-time. Space-time consists of 4 dimensions, 3 of which are dimensions of space. These include left and right, up and down, as well as forward and backward. The fourth dimension is the dimension of time. The dimension of time only has one direction, unlike the other three dimensions. The terms u and v in the general relativity equation can hold four different values, which are 0, 1, 2, and 3. The value of 0 represents the dimension of time, while the values of 1, 2, and 3 represent the other three dimensions of space. Hence, the equation is able to take on 10 different forms with all the different combinations of values. Okay, I'm not going to delve too deep into general relativity because I have a time limit and Mr. Ferguson gets bored easily. However, I have much more information on general relativity and other topics on my website if you are interested. So let's talk about Karl Schwarzschild's crucial equation, the Schwarzschild radius. According to this equation, anything can become a black hole. Mathematically, you could compress anything into a small enough area to turn it into a black hole, and that is the essence of what the Schwarzschild radius truly is. If you compress the Mount Everest into a nanometer, it would become a black hole. If you compress the Earth into the size of a peanut, it would become a black hole. Alright, now that we got the math done, let's talk about perhaps the most interesting part, the actual journey through a black hole. So what happens when you enter one? Monosyllabically, death. Polysyllabically, first of all, you really won't be able to experience the effects of a black hole from that close. Your body, or rather body parts might, but you won't be able to perceive anything going on because you'll be dead. Let's say Christopher Arjun gets sucked into the black hole. Once he gets to the event horizon, he will begin to feel the attraction from the singularity. Christopher will notice an irregularity regarding how much attraction he is experiencing. Whatever part of the body is closer to the black hole will feel a greater attraction than the body part furthest away from the black hole. So assuming Christopher is going to the black hole feet first, his body would look something like this. It will be stretched and elongated as the feet get pulled in faster than the part of the body above it. His molecules will be violently ripped and stretched apart. The rate of increase in speed also increases for the body part closer to the black hole. So as Christopher gets closer, the intensity of the stretch increases. In scientific terms, this process is called spaghettification. Spaghettification is the vertical stretching and horizontal compression of objects into long, thin shapes in a very strong, non-homogeneous gravitational field. This term is used to describe this process because your body stretches out and starts to look like a piece of spaghetti. Also, don't be mistaken, spaghettification does not only happen if a human enters the black hole. In fact, any object entering the black hole will experience this. Whatever is closer to the black hole gets pulled in faster, consequently causing spaghettification. In order to understand this better, we can also take a look at the Earth and its tides as an example. Whatever part of the Earth is closer to the Moon will have a stronger gravitational pull from the Moon. The attraction gives us high and low tides. Although the Moon's gravity is nowhere near strong enough to spaghettify Earth or vice versa, we are able to notice the impacts of gravitational pull depending on the position of the two masses, which hopefully allows us to understand spaghettification better. This is also why the forces of gravity causing spaghettification can be referred to as tidal forces. We have already talked about what a black hole looks like, but let's get more specific. While you get sucked into your demise, let's say our friend Het Patel is watching this happen. In Het's eyes, you will simply slowly approach the event horizon. Once Christopher crosses the event horizon, no light will be able to escape, and Christopher will appear frozen to Het. After some more time has passed, the light coming off of Christopher will start to appear red due to it being redshifted, and Christopher will eventually fade away. Het will never be able to see Christopher actually cross the event horizon, and consequently, Het will not be able to see the effects of spaghettification because that starts to happen once Christopher crosses the event horizon. When that happens, the light cannot reach Het to show spaghettification. Now, let's get back to Christopher's perspective. As he continues to approach the black hole singularity, his view of the universe will get compressed into a smaller and smaller space behind him. Since both Het's and Christopher's perspective will be happening at the same time, it would be like Christopher is in two places at one particular time. Now these will just be two different perspectives, and there won't actually be two Christophers because of quantum physics. Anyways, once Christopher gets further into the black hole and reaches the singularity, we don't really know what will happen. All the laws of physics and the world as we know it will cease to exist. Our world works according to applied restrictions, certain laws and concepts. Well, not anymore. Nothing we know about the universe will apply, and it will truly be a bizarre place. This is where the various theories that haven't actually been proven yet come into play. Now, truth is relative, and everything that we believe to be true in science is essentially just a theory that has been proven through many well-planned out experiments. Black holes are of course no different, and they are actually one of the things that we know least about. I mean, experimenting on a black hole is quite difficult. So let's talk theory. This next one has no evidence to it, so in no way is this a fact, but I thought it was extremely interesting and I wanted to tell you about it. Some people theorize that when you enter a black hole, you come out from a white hole. Basically, you will come upon a second event horizon after passing through the first one, which has a singularity that repels rather than attracts. The singularity that attracts is part of the black hole, and the singularity that repels is part of the white hole. From here, the theory provides two possibilities. The first possibility is that this second singularity will repel you into another parallel universe. The second possibility is that the black hole and white hole will act as the entrance and exit to a wormhole. I really hope that you guys learned something today and weren't too bored with this video. Anyways, just remember, don't call me when I'm recording. Thank you for your time and attention. Bye.